last time we talked about DDP, some kind of details there and how to deal with constraints. We didn't quite get to doing minimum or free time stuff with DDP, so we'll finish that off today. And we're going to start talking about direct trajectory optimization today. And along with that, kind of the standard method for solving those problems, or one of the standard methods, is called sequential quadratic programming. And then we're going to talk a bit about direct collocation, which is a kind of a very classic and very standard algorithm. That's used for lots of things in the aerospace world. Like this is how you kind of like design trajectories to fly to Mars and the moon and stuff like that. Cool. So any questions about anything before we kind of get into things? Nobody? Everyone's good? So a couple things that have been coming up in office hours that I wanted to kind of just hit really quick. Notes on like linearizing in the context of LQR and MPC. So when we use linear dynamics models, right, we're taking something that looks like, say, xk plus 1 equals f of xk uk. We're finding some nominal sort of trajectory or nominal state that we want to keep things in. And we Taylor expand this whole thing. So we turn this into, say, xk plus 1 plus delta xk plus 1 is approximately f of xk uk plus a delta xk plus b delta uk, right? And what we then do is say, okay, well, this term, this guy here is the same as this from the original dynamics. So we're left with this delta system, right? That says delta x k plus 1 equals a delta x k plus b delta uk. And to be super clear, right, this a is partial f partial x, and this b is partial f partial u. And then we get this sort of canonical, ax plus bu linear system that we talked a whole bunch about, that is kind of the dynamics that we use when we do LQR for sure, and also the dynamics that we use in a lot of MPC stuff when we do convex MPC in particular, right? So this apparently came up a bunch in office hours and for this homework. So just wanted to like keep it sort of extra clear to go over this. So the thing to know here is when you're doing LQR, for example, we're computing a feedback matrix based on these delta dynamics. So when you get that K matrix out, what you're really going to do is you're going to have delta U equals minus K delta X, right? So when you're running this on a nonlinear system that you've linearized, you might have a nominal U, like a U naught that you're applying to the system. And you might have a non-zero X naught as well, right? So when you're doing this on a nonlinear system in general, you're going to take this, compute the delta U, but the actual U you apply is really going to be U is some U naught, the nominal U, right? That was the feed forward U, say, the U that was in there before we added the delta U, minus K, and this delta X, right, is going to be whatever the nominal X was, sort of minus it's the actual X minus the nominal X, right? Does that make sense to everybody? So like you have to tack on or deal with the reference or nominal values of both U and X in these things, right? And this applies on the homework in particular, right? You want to think about this when you're doing LQR, and you also want to think about this in the MPC stuff. When you're doing MPC, if you're using a linear model like this, you got to think about sort of, there's probably a reference value, right? So in particular, think about the rocket stuff. there's a nominal reference u that's, sort of canceling out gravity and stuff like that, right? And you're really computing these delta values. Cool. Any questions about this? Okay. Hopefully that's clear. Okay, so to sort of just finish up the discussion we were having last time, let's do the sort of free/minimum time thing really quick. So these show up in quite a few applications. So anyone have any thoughts on where you might see something like this? Nobody? No ideas? No. Okay, so minimum time is get to the goal state as fast as possible. And usually that's classic bang, bang optimal control. That's saying basically what you want to do is full gas and then full brakes. And you'll get out this kind of bang, bang policy. So that's minimum time. In practice, those aren't used a whole lot because they do tend to do crazy things that are difficult to track in practice, basically run the system right up to its limits. You probably don't want to do that in real life for various robustness reasons and safety reasons. But the free time thing does come up a lot. So it comes up in, for example, situations where like you care about getting to some goal state at the end of your trajectory, but you just don't necessarily know how long it's going to take or when you might get there, right? And so, I mean, you can imagine all kinds of scenarios where this could happen, and is a fairly common thing. So in that case, what you want to do is not necessarily have, pre-specified length of the trajectory, pre-specified time steps. Instead, you want the solver to kind of figure that out for you, right? So the classic minimum time problem is actually the following thing. We'll just write it down, I guess. So you'd have like in continuous time, which we don't usually talk about, you'd have this kind of deal. Your cost function would actually just be integral from 0 to big T of 1 dt. So as you can see, right, and then your T, your big T, the limit of the integrand is a decision variable that you're optimizing over now, right? And so this thing will just integrate up to T, subject to, the usual stuff, dynamics. And then like maybe some goal state. And then maybe, in fact, definitely you're going to need control limits on this. What happens if I don't have any control limits on this? Yeah, you'll get like so it's very easy to set up ill-posed problems like this where there's not a finite solution, right? You can get garbage pretty easily. So this is kind of the classic minimum time problem. And sometimes you can actually get these answers in closed form, like if there's linear dynamics and things like that. Yeah.
Is it common to set this up as a multi-objective optimization where you like have minimum time, but also some weighted like cost on your fuel usage?
Yeah, you can totally do that. I mean, so this is just an example, right? I can easily throw whatever I want in that cost integral in addition to time, right? And weighted and so yeah, you can absolutely do that. Yeah.
Sorry, what's the subscript on the x of big T equals?
X of,
goal.
Oh, X goal. Yeah, sorry. Okay, minimum time, cool. Okay, so here's kind of the idea, right? If we solve this numerically in a computer, so like the way we kind of do it now, we have fixed time steps, right? So if I wanted to do something like this right now, I would be actually wanting to like minimize the number of time steps, which would mean like the size of my decision variable vector in my optimization problem is changing, which is bad. I don't want to do that, right? So we don't want to change the number of not points. What should I do instead? Anyone have any thoughts? How would you do this if I said, okay, I want to use the same number of not points? Like, what do you have to do then? It's kind of the, yeah, we've got to change the time step. So like in the kind of current optimal control setup we've been playing around with, like the DDP setup, like how do you think you would set that up then? No, so this is a variable horizon, you know. We're going to have fixed number of time steps. We want to make, basically what we want to do is change the H's, right? And let the solver figure that out. Yeah, do you have an idea? Yeah, so not pretty much, yeah. So what I'm going to do is I'm going to make the H's, the individual time steps at each stage or each not point. I'm going to make an input in the U, and then I'm going to add a state on that integrates up the total time to the dynamics. Does that make sense? Cool. So basically the H in your RK method becomes a control input. So you end up with something that looks like xk plus 1 equals f of xk, and we'll call this, I guess, u tilde sub k, where this u tilde is the original u sub k, and then the h at that time step. And then you can sort of do, you know, you can rewrite that, like that f is still your Runge-Kutta step. It's just now that h is also an input. And then you probably also want to scale the cost by h if you're using some multi-objective cost. Yeah.
Doesn't the time step we're using affect the discretization like A and B? Do you have to update those every time you change H?
Yeah. So this is exactly, yeah. So even if your dynamics are linear, if you set it up this way and you solve a minimum time problem, it's non-convex. Like the discretized dynamics with the H as a decision variable are no longer linear. Yep, absolutely. So this is always a non-linear thing. There are some caveats that if anyone's really into this and you want to, there's actually a convex reformulation of the linear dynamics minimum time problem. Fun fact, we could talk about it offline if you're curious. You can also, yeah, so the other thing here is also can scale the cost. So you could do something like this if you had other terms in the cost function. So you could do j of, say, x tilde u tilde would be sort of hk times your whatever your original one-step cost was. So this is basically doing, you know, like classic rectangle rule integration of that integral cost thing. Okay, so yeah, like we just said, this is always going to be nonlinear, non-convex, even if the dynamics are linear. There's one more quirk to this. Does anyone have any idea what can happen here? So I'm using this like discrete Runge-Kutta thing. And as we kind of saw, right, weird stuff can happen in a Runge-Kutta method as a function of time step, right? So we saw how, you know, you get artificial energy weirdness happening as you make the time steps really big and all this kind of stuff. So if I let the solver pick my time step, weird things can happen, right? In particular here too, not only do you have to worry about making them super big, super small, they can even, if I don't do anything, if I just set this up and do standard DDP with this, like we've been doing, there's nothing to stop H from going negative either, right? Which would be extra weird and terrible. So generally speaking, you need to do this, you need constraints on the H's to make this work at all and for it to not just give you garbage. And usually what you want to do is bound H within some limits that you think are reasonable given your system dynamics and the Runge-Kutta method you're using and stuff like that. Otherwise, basically what will happen is the solver will exploit sort of errors in the dynamics, right? Like it'll, for example, make one time step gigantic and then one super tiny and one negative or something like this, and exploit discretization error to like get lower cost. So you don't want that. So yeah, you can call this like cheating physics. Okay. Any questions about any of this stuff? Yeah.
Is there a reason why the H is in the controls and not like the state?
So pretty much because I want to optimize it. So in DDP, I have X naught, and that's all I get to pick, right? And I get to then, like, I'm finding the U trajectory, right? So if it's something I actually want to, play with, I kind of have to put it in the U. There's one other option, which yesterday, remember we talked about this whole idea of like putting random parameters into some U naught that you sort of tack on ahead of the trajectory, and that lets you do parameter optimization. You could go that route, where you basically pick one fixed H for the whole trajectory and then like backprop it through the whole trajectory and then optimize it in that U naught. It turns out, like we kind of talked about 2 days ago, that gets pretty ill-conditioned. And it turns out this setup where you let it vary at each time step separately works a lot better. It's like just numerically the better way to go. All right, cool. Everybody on this? Yeah.
So in this method, we're optimizing H at like each individual time step.
Yeah.
So is that to, I guess, so is the goal of this just to kind of maximize like machine effort, like to make it faster, or does it like kind of improve like the accuracy of the result itself?
It makes it, so you mean basically letting each time step have its own H versus having one global H?
Yeah.
Yeah, so if you do one global H, what you can do with the kind of stuff we talked about last time, where you kind of tack on this additional fake U at the beginning. If you do it that way, you get this kind of like ill conditioning, vanishing, exploding gradient, tail wagging the dog kind of effect, because it's affecting the entire trajectory. And it's this one parameter all the way at the beginning. So you have to backprop the gradients and Hessians of that stuff all the way along the trajectory. Whereas if you do it at each time step individually, it's one time step at a time, right? So you're not getting the same sort of error, sort of ill conditioning sort of thing happening where you're backpropping all the way along the whole trajectory. Does that make sense?
Yeah.
Cool. Yeah. So it's basically this way is numerically better, practically better. Mathematically, they're totally equivalent, right? And if you had some magical infinite precision computer, maybe you'd want to do it the other way. But if you're doing this on a real computer with floating point arithmetic, this is kind of the better way to go. All right. Everybody good? Yeah. All right. Next up, we're going to start talking about direct trajectory optimization. So this is basically the other way to do trajectory optimization. Like we did all this indirect ILQR DDP stuff. That stuff's super widespread, super common in robotics. Then the other way to go is this direct stuff, which is also super common, super widespread. Funnily enough, most organizations that do this stuff, like labs in academia or companies or whatever, have like a culture of basically preferring one or the other. Like you'll find a lot of labs are either direct labs or like DDP labs and have their own in-house solvers for doing stuff and kind of stick to one or the other. So I don't know. Okay, cool. So the basic idea here, in a lot of ways, this is more, it's easier to like conceptualize and it's easier to kind of write down a lot of this stuff in this setup, and it makes a lot of sense, but implementation wise, it can get a lot hairier. So the basic idea here is to just take the original optimal control problem we wrote down with the cost function and the dynamics constraints, just discretize everything and feed it to a solver. So that's sometimes called transcription. You'll hear that called direct transcription sometimes. So let's write that down. So yeah, you take the original problem you had, and in the most straightforward, direct way possible, you just like discretize it and then feed it into a computer. And these are going to be what are called nonlinear programs, or NLPs. This is not for the CS people. This is not natural language processing. This is yet another overloaded acronym. Nonlinear program, which is just stands for like a generic nonlinear smooth optimization problem. So there's no convexity or any of that nice stuff. Generally, these have the form. So here's what an NLP looks like in general. min over some x, f of x subject to some constraint, equality constraints, c of x equals 0, and then some inequality constraint, say d of x less than or equal to 0. So that is it. That is a standard form NLP. So we're basically just take our optimal control problem and like discretize, do whatever we got to do to get it to look like this. Just some notes. This is called the objective function or cost function. And then these are, for us, these will be the dynamics constraints and the equalities, maybe a goal constraint if you want, but generally this is where you're going to put the dynamics. And then here is going to be maybe, you know, like other constraints like torque limits, obstacles, that kind of stuff. Okay, so the point of this is that standard form is what the solvers will take. So you find there's lots of NLP solvers. We'll talk about a couple, we'll use a couple of them. They basically all take problems that look like that and have a few requirements on the functions. Like they basically have to be, generally speaking, C2 smooth. So you have to be able to take gradients and Hessians. But as long as they look like that and they're smooth and you can get the derivatives, if you can hand that to a solver, it'll solve it for you pretty much. Okay, so what like off the shelf, right? So the other thing about this is the large scale part. So when we do this optimal control stuff, like usually we're doing stuff with thousands of decision variables, not uncommon to get into tens of thousands or even hundreds of thousands. So they're not large by machine learning standards, but they're like pretty big. They're big enough that like your own cartoon, you know, MATLAB or Python version of one of these is probably not going to cut it. So that's why there are these kind of large scale off the shelf, you know, commercial solvers and stuff like this. And there's a few common ones in particular. So has anyone done any of this stuff before? Yeah. What have you used?
IP opt.
Yep.
Is the main one that like is our competitor. I mean, we have like an in-house solver that's the benchmark.
Yeah. Interestingly, IP opt from CMU.
Oh, really?
Yeah. Gurobi is a convex one, not an NLP solver. So the big ones are, yeah, definitely IP opt, which is open source. So that's kind of the main free one that you can just download. And that, again, it's from a lab here at CMU. The other really popular one in optimal control, at least, is SNOPT, sometimes pronounced SN opt. I've heard people say it that way, which is commercial, as in not free. And there's another one called Nitro that's also kind of popular. That's also commercial. So these are things like you buy it or you install it, right? And they'll solve things with like 100,000 variables for you, as long as you can set up the problem, kind of hand it the derivatives and stuff like that. Okay, so that's the way this is typically done. The way most of these solvers work, or there's many details, but like a common strategy that's used in a lot of these solvers is something called sequential quadratic programming, which we'll talk about now, which kind of is not surprising at all when based on the name. So let's see. Also known as SQP. So we've already seen quadratic programs, right? We're all good with that. Quadratic objective, linear constraints, linear equality and inequality constraints. So what do you think sequential quadratic programming means? When we have a nonlinear program like this, basically what you're going to do is take the nonlinear program and take a second order Taylor expansion of the cost, and linearize the constraints to get a QP, solve the QP, use that to get like effectively a Newton step, right? And then like do it again. So yeah.
So I'm still like just like struggling a bit to understand the difference in this and what we were doing before. Is this like a generalization of what we did before, or I guess what is the?
So this is another kind of class of algorithms for solving the optimal control problem. So when we looked at the optimal control problem, right, which is like minimize some costs, you got your dynamics, whatever. And we looked at, you know, we did, if it's linear, you have LQR, right, all that good stuff. And then we did, if it's nonlinear, we had this iterative LQR DDP stuff, right, that was based on these dynamic programming sort of forward backward ideas. Here instead, we're not going to do anything dynamic programming. We're not doing forward rollouts, backward recursions. We're literally going to take the optimal control problem and like write it down in this form, this like standard NLP form. And we're going to get into that next, like how to actually set it up like that. And then you're basically going to take it and hand it to a solver, like generic nonlinear programming solver, and that's going to get you an answer. So that's kind of the details here and how you discretize. And there's a few standard algorithms that are based on like the details of the discretization, which we're going to get into. Basically, you know, when we did it before, we just said RK4, you know, that's probably what you want. Here, it's a little more subtle. You generally don't want RK4 here. There's other things to do that are called collocation, which we're going to talk about. And that's really it. Like basically, there's some tricks in how you set it up like this, how you discretize it. Once you got it to look like that, then you just use a off-the-shelf large scale solver. Does that sort of make sense? Cool. All right. Okay, so let's do this SQP thing. So basic strategy is to use a second order Taylor expansion of the cost, or really of the Lagrangian, and linearize the constraints. So linearize C of X and D of X to approximate that NLP as a QP. So local, you know, QP approximation, and it's going to end up looking like this kind of deal. And again, these are deltas, just like we had this whole discussion before about when you linearize, you're really talking about deltas. So we're going to do this Taylor expansion in terms of some deltas, and we're going to get something that looks like this. So we'll have like whatever our original C of X was plus this big C will be the, you know, the linearization, the Jacobian, and then the D, similar thing. Where, you know, all those matrices are sort of what you expect. So this thing is the Hessian of the Lagrangian. This thing is the gradient of the Lagrangian. This is the Jacobian of the equalities. And then the D is the Jacobian of the inequalities. And for, you know, for completeness here, the Lagrangian is what we wrote down before, where you've got your cost function, and then your Lagrange multiplier for your equalities, and then your Lagrange multiplier for your inequalities. So you do that, you sort of have some guess, take your big Taylor expansion, linearize, quadraticize, get a QP, solve the QP, and now you've got a search direction, just like when we did Newton before. So you'll solve that QP, you'll get some search direction thing that looks like this, where you'll have like a, you know, a delta X, a delta lambda, a delta mu, right? And then you're going to do a line search on using that search direction, just like we talked about before with a merit function. Okay, question. What is different about this than like the Newton stuff we did before? This looks pretty much exactly like the whole Newton thing we've been talking about all along. What is the difference? Why is this sequential quadratic programming when the stuff we did before was just Newton's method, where we solve for like a, you know, a delta x and a delta lambda?
Relinearize every time step.
Yep. Which we did before, right? Yeah. So what's different here?
That we don't do these backward pass and then forward rollout.
So yeah, that's true. I mean, but this, I'm talking about in the very beginning of the class, we were just talking about optimization and, you know, Newton's method and how to, you know, solve things with merit functions and regularization, that whole conversation about generic optimization stuff. What's different here versus that like Newton KKT stuff we did before? You don't have any ideas? So when we at the beginning of the class, we talked about like inequality constraints and how that was kind of hard, right? And we talked about augmented Lagrangian methods, and we did this KKT thing and whatever, only with equality constraints. So the difference here is this has inequality constraints. So, and we said at the beginning kind of how inequalities were a lot harder to deal with than equalities. And that's kind of spawned this whole conversation about interior point methods and augmented Lagrangian methods, right? So here, what you're basically doing is saying, I can linearize everything. And when I linearize those inequalities, like I just get a QP. And I have some other method for solving the QP with the inequalities that I like. Could be anything, right? And we made one, right? We made a QP solver. So if you have a QP solver, then you can take an NLP, approximate it as a QP like this, and make progress and solve it. So the difference here is this has inequality constraints in addition to the equality constraints. Does that make sense, everybody? Okay. And there are some sort of subtle gotchas, as you can imagine, in like actually implementing one of these things, but this is kind of the general story. If I take away the inequalities and just have, so if there's no D, it's only the C, then it is exactly, it reduces to what we did before. Yep.
If we add slack variables to the inequality constraint and put the slack in the objective function to minimize,
yeah,
that would make this exactly the same as the Newton KKT.
You can do stuff like this. So do you want to be a little more specific? Like, how would you make that happen? So you want to turn the inequalities into equalities by introducing slacks, is what you're saying, right? So there are ways to do this. Yeah, do you have an idea?
So like add a small, like a slack variable which is positive, or like, yeah, which is positive.
How do you do that? If I need to enforce that the slacks are positive, I have an inequality again, right?
Yes.
So that didn't help.
Like a square.
Yeah, there you go. So that works. So it turns out that doing it, what you're saying, is actually one of the classic ways to derive the KKT conditions and prove them, is by introducing a squared slack and turning the inequalities into equalities. It turns out practically, if you want to write a solver, it's terrible. It doesn't actually work numerically very well. But there are places where it does work, and people do, on the margins, you can do things like that. Yeah, so that's not a bad idea. It's actually very clever. And there are ways that is useful. It turns out if you're implementing like real industrial strength stuff, it doesn't work very well. But yeah, good question. Okay, cool. So yeah, basically, if you just have the equalities, is what we did before. So like you get your classic, like, you know, KKT system thing with the delta X and the delta lambda and sort of those gradients over here. All right, so we did this at the beginning of the class, right? As a refresher. And this is the KKT system. So it's just that. So if I only had dynamics constraints, it would just be what we did before. The thing that makes it harder, and the reason it's sequential quadratic programming and not just Newton's method, is the inequality constraints. that get sort of passed down that make it a QP at the lower level and not just this sort of classic KKT thing. Okay, so to belabor that point some more, you want to think of this, think of SQP as basically just a generalization of Newton's method to inequality constraints. And in principle, you can use any QP solver you want to solve that subproblem, that QP subproblem. But most good implementations have a lot of kind of fancy, basically in good industrial strength SQP solvers, the QP solver, the low level QP solver and like the upper level SQP stuff are extremely tightly integrated. And there's lots of tricks to make them work well. And in particular, good implementations usually use active set strategies for the QP. Because that lets you play lots of tricks with warm starting. So like we talked about this in the, back in the beginning, like the active set thing is you're trying to guess which inequalities are active and treat them as equalities and then throw out the inactive ones. And if you can guess really well, then this is really good. The reason this is good in an SQP solver is you can imagine if you're doing this, you're iterating a whole bunch and relinearizing. A lot of the times on a lot of problems, the active set doesn't change much at each iteration. And when you get towards the end, when you're almost, it doesn't change at all. So if you do this active set stuff, it lets you warm start the QP solver and converge faster and stuff. And there's lots of good tricks. Okay, what else is there to say? Okay, so the other thing to say about this is to get any kind of like reasonable performance using these kind of things, you have to take advantage of sparsity in the KKT system. That is essential. Sort of DDP and ILQR really like implicitly are already doing this stuff. They're really like harnessing the structure of the problem. If you kind of treat it this way as a generic nonlinear optimization problem, if you do this naively, like you just can't solve the linear system, it's too big. So you really need to worry about the sparsity stuff. And most of these commercial solvers are set up to try to like automatically figure out that sparsity stuff for you and do a good job. So yeah, SNOPT in particular is good at this. That stands for, maybe unsurprisingly, sparse nonlinear optimizer. And that's kind of why it's popular for this stuff. What else is there to say? So there's some other things you can do here. So we did SQP. If it happens that the inequality constraints are convex, like nonlinear but convex, so like conic, for example, would be the main one that we would talk about. You can actually just pass those down into the subproblem and do, instead of SQP, SOCP or whatever, you can do sequential convex programming, where you can basically anything that's convex, you can just throw into the subproblem and then linearize the rest. So that's a thing now that people are into. So maybe here, if you read any of the literature, you'll see SCP a lot. Sequential convex programming is kind of a hot thing the last few years in optimal control. And as an aside, yeah, that's sort of a recent thing. That's kind of an active research area right now, or for the last like 5 years or so, I'd say. And probably not so common like in industry at this point. Okay, cool. Any questions about any of this stuff? Yeah.
Is that something that you have to specify, or does like solver just determine?
Yeah, it's definitely something you, at this point, it's definitely something you would have to manually kind of specify. Yeah. I don't think there are any like large scale off the shelf SCP solvers in the same vein as like IPOpt or SNOPT at this point. It's like a research thing. So generally these are like homebrew things that various research labs have built where they're using some off the shelf convex conic solver and then wrapping around it the infrastructure to do the linearizing and approximating stuff. Yeah.
Can you explain what do you mean in the last part when you said where inequalities are passed directly to the subproblem solver?
Yeah, so in this generic setup, like where everything's assumed to be nonlinear, like the SC and the D. Okay, so if D is like, say D is a cone, that's convex, right? And we already know that that's convex, and there's nice conic solvers that can handle that directly. If you're doing SQP though, it's not able to do that. So if D was the cone, if I'm doing SQP, I would end up linearizing that D constraint and like approximating it, whatever. If D is a cone though, and we know it's convex, there are good solvers for that, right? That can solve the cone directly. So what I could do is, if C is my nonlinear dynamics, but D is a cone, I can actually just linearize C and then keep the exact cone D in the sub problem, right? Because it's convex.
Yeah, take advantage of the convexity of the.
Exactly, yeah. So if D is convex, if D is nonlinear but convex, then we can keep it. We don't have to linearize it, right? That's the idea. That makes sense? Cool. Anybody else? Okay, so that's sort of high level overview of this stuff. Now we're going to talk about kind of basically, besides DDP, the other like main super classic algorithm. Yeah.
Back to before, how common is it to like have problems in like this space where you don't have a good like feasible initial guess, or do you pretty much always have a good feasible initial?
No, it's pretty common, I would say. I mean, it's very common, in robotics, motion planning, et cetera, to have situations where it's even if you could generate a feasible initial guess, it's actually not always a good idea either. We're actually going to do that today. That's like part of this deal. These methods are really good at doing infeasible starts. That's one of the main advantages. So does that answer? Yeah, cool. Okay, cool. So here we go. Direct collocation. Has anyone heard of this before? Nope. I already asked this, didn't I? I'm sleep deprived. Okay. So what is this all about? Okay, so basically, so far we've used explicit Runge-Kutta methods. Like RK4. To discretize our dynamics. And what explicit really means is there's some function that sort of, I plug into and I get xk plus 1 out of it directly. So I have stuff that looks like this, right? That's what happens when I do RK. So these methods, I had you play around with on the first homework, some implicit methods too, right? We did like implicit midpoint and you saw what that looks like, and you have to use Newton's method to sort of figure out what the xk plus 1 is, which is maybe annoying. So the punchline here is these explicit methods are probably what you want, or they're at least computationally, nicer if you're doing a forward rollout, where you're just trying to simulate forward in time, right? Because if you're using an implicit method, you have to sit there and do Newton iterations just to get the next time step. So explicit is nice for doing a rollout. However, if you're doing this direct stuff, there's not really any advantage to using an explicit over an implicit method, computationally speaking. Because I'm going to just take everything and treat them as generic equality constraints in some big NLP solver. If I'm doing that, I can write down those equality dynamics constraints as implicit Runge-Kutta or explicit, and it doesn't matter. It's all kind of all the same. And the big trajectory optimization solver can take care of the Newton stuff for me to find the solution to those implicit dynamics constraints. So let's talk about that. So in a direct method, you have your dynamics enforced as equality constraints. Between knot points, there's no real advantage. So in particular, right, in one of these collocation type methods, I can write down a dynamics constraint CK, say, that looks like this: XK, UK, XK plus 1, UK plus 1 equals 0, right? My constraints look like C of X equals 0. So I can just write something like this down where, you know, XKs and XK plus 1s and whatever are all buried inside this nonlinear function, like in an implicit method. And I just hand that to the solver as is, and it takes care of it, right? So there's no advantage, you know, for being explicit in this context. And in particular, like, because of that, right, the implicit methods actually have a lot of things going for them. They tend to be more stable, they can have better energy behavior, and they can generally be more accurate for the same order. And there's even more fun tricks you can play, which we'll talk about now. So, okay, what collocation methods do is represent the trajectory as a bunch of, as polynomial splines. So in particular, the super classic version that we're going to talk about right now uses cubic splines. So at each, you know, between xk and xk plus 1, you're going to fit a cubic spline between all the knot points. And then enforce the dynamics with equality constraints. So basically, if I write a cubic spline down between xk and xk plus 1, I can take that cubic polynomial, I can take its time derivative, right, in closed form, and then I have some spline for x dot, and then I can just enforce my dynamics on that derivative, right? So we'll do this out. So the classic, what's called Dirkall algorithm, the direct collocation, uses cubic splines on the states. And turns out uses piecewise linear interpolation, aka first order hold. For the U's. I don't know, that's just what it is. There's some commentary on this in the original paper. It's Hargraves and Paris from the mid 80s. And this was first invented. And yeah, they have some comments about like they tried other stuff and like using higher order on the U's didn't provide any advantage. So they did this. This is the classic. You can use whatever order splines you want. I would say in robotics, Dirkall is extremely common. You'll see that a lot, but I don't see really people doing higher order stuff so much in robotics applications. In aerospace applications, though, you will see sometimes super high order polynomials for doing long space trajectories. And the reason is really those trajectories are super smooth. So using polynomials, high order polynomials works really well. A lot of robotics applications, you've got like impacts and friction and non-smooth stuff. So using really high order polynomials to approximate that stuff doesn't work super well. It's kind of my take on why that's probably not a thing. So. This is the one you will see the most. So here's how Dirkall works. You have your state trajectory. So we'll draw some like cartoony x of t. So say you've got, I don't know, something that looks like this. And let's say this is xk over here. So this is tk, this is xk. And then let's say over here is xk plus 1. And this is tk plus 1. These are what we're going to call knot points. This is where that lingo comes from, by the way, that I keep using. So knot points. And then we're going to have also sort of the midpoint in the middle here, which isn't going to be part of our decision variables at all, but we're going to compute it as part of the constraints. So we'll call this like, I don't know, tk plus a half, something like that. This thing is called the collocation point. Basically the midpoint on the spline. And we can evaluate it using the spline function. And then we can enforce the dynamics at that point. That's why it's called the collocation point. Okay, so that's how that works. And we're going to write out the math for that in a sec. And then you also, on the U's, you're just going to have kind of the piecewise linear things. You'd have something like, like this, say. Not super interesting. Cool. Okay, so let's write out a cubic spline. So we have, over a given time step, you're going to have something that looks like this. We're just going to write out kind of a generic cubic function. With kind of unknown coefficients. And in general, right, like if I have a big state vector with, you just do one of these for each element of the state, right? Okay, so I can write this down and then I can just differentiate this also in time. So I can get a similar thing for x dot of t. And it's just the unsurprising thing. I can still do basic calculus, I think. Okay, cool. So we get that. And now the gain here is now I can write both of these as matrix equations in the coefficients. So I can take, for example, if I'm writing both, like my typical dynamic stuff with both x and x dot, I can stack all this up in a matrix equation that looks like this. If I have the C's in here, so C naught, C1, C2, C3, and I did that wrong. What I want to do is evaluate these things at the endpoints. So I want to evaluate both x and x dot at time k at the knot point. So I've got xk, x dot k, and then xk plus 1, x dot k plus 1. So I can evaluate this stuff. I just plug in, for xk, we'll use t equals 0. For xk plus 1, we use t equals h. I can plug all that stuff in and evaluate the coefficients on the polynomial and kind of just write that down here. right? And then I can actually just solve this linear system the other way for the C's. So what this is telling me is, given, if I know the state and the state derivative at the knot points, I can solve for the polynomial coefficients and get the polynomial spline that interpolates these guys. So I'll write that out real quick. It's just inverting this matrix, which you can do in closed form. It isn't too bad. And that spits you out these coefficients. And then you can do whatever you want on the polynomial. That's kind of the idea. So this looks like minus 3 over h squared. It's 2 over h over h. Okay, so you do this. And now, once I've got those coefficients, I can evaluate that spline. Don't worry about copying down all my scribbles, by the way. I post all this stuff and I'll post the code. So that's kind of, I don't want you guys trying to read my awful handwriting in real time. It's not a good thing. I apologize, but yeah. Okay, cool. So, so now we can evaluate this stuff wherever we want. And in particular, we can evaluate it at this time tk plus a half, now that I have the coefficients, right? So I plug in the knot points, fit the spline, then I evaluate the spline in the middle. So I get stuff that looks like this. Okay, so that's what I get if I just plug into the spline. This is an 8. And now what I'm going to do is plug in the dynamics for the x dots. So I'm going to get the following thing. And then similarly, I can evaluate the x dot stuff at that collocation point. And I'm going to get, just right off the spline, I'll get something that looks like this. And then again, I plug in the dynamics. Plus. Okay, so that's the dynamic stuff evaluated at that collocation point in the middle of the spline. And then the controls, we're doing linear interpolation, so that's super easy. So I get uk plus a half equals sort of u at tk plus h over 2. And this is just the average of the uk's, right? Because it's linear interpolation. Okay, so now I have all the pieces that I need. So here's the dynamics constraints. So this, so each of the, we'll call these CIs, each of these dynamics constraints and the big C that's going to go in our nonlinear program are going to look like this. They're going to connect pairs of knot points. So xk, uk, xk plus 1, uk plus 1. And we're going to have like n minus one of these, right? They're going to connect each pair of time steps. These are going to look like the following thing. F at x k plus a half u k plus a half. So the stuff, evaluated appropriately there, which is, this is coming from here, right? This is x dot at the midpoint, which is our dynamics at the midpoint. I'm just going to plug everything into that equation, right? So that equals, or we're going to write it minus 3/2. Okay. And to be super clear, right, this is the x dot. These are all the continuous dynamics functions. These are not like discrete time, whatever, coming from Runge-Kutta. These are the original continuous dynamics functions. So to recap, what we did here is we assumed there was a cubic polynomial connecting, xk and xk plus 1. I analytically diff the cubic to get like what x dot should be, right? So I have x and x dot at both knot points uniquely fits a cubic, right? If I give you x and x dot at 2 points, that's four numbers, and that's how many undetermined coefficients there are in a cubic. So I use that to go fit the undetermined coefficients on the cubic. Now that I have that, I can plug in t equals h/2 and get the midpoint on the cubic, and I just evaluate the dynamics at the midpoint of that cubic. That's how I get this stuff, and I just plug everything in. So what I'm doing is like enforcing the dynamics constraints. Basically, I'm forcing the ends to be connected between the successive splines, and I'm forcing the derivatives to match, right? Between pairs of splines, that's kind of how you set splines up. You match the value in the first derivative so they connect nicely. And then I'm enforcing the dynamics at the midpoints. That's the whole deal. And that gets me kind of a unique thing. And it turns out that gets me a third order accurate integration, like a third order Runge-Kutta method. So we derive this in a weird way. It turns out this is totally equivalent to a third order implicit Runge-Kutta method. These are Runge-Kutta methods at the end of the day. They're just kind of weird ones. So some more notes. Let's see. Only the sort of xk and uk are decision variables. Not the sort of collocation point things, not the halfway values. We kind of compute those on the fly inside the constraint function from the spline, but they're not actually decision variables of the problem. So this whole integration scheme is called Hermite-Simpson integration. For reasons that I don't think are very important. Basically, these cubic splines are called Hermite polynomials for some reason. And the Simpson's rule is basically when you integrate a cubic, when you integrate a cubic polynomial in closed form and use that to like approximate an integral, it's called Simpson's rule. I don't know. So some old guys 300 years ago came up with these things, and their names are forever attached to optimal control, even though they died long before any of this stuff was done. So, cool. Good for them. This is third order accurate. And the big reason this is the whole reason this is a thing in optimal control is that this requires fewer dynamics calls, it turns out, than explicit Runge-Kutta. And we'll talk about that hopefully you can see this in a sec. This is actually pretty slick. And maybe not obvious based on how we wrote it down. So if I wrote down like explicit RK3, I need 3 dynamics calls per time step. Like we've seen, this is not a surprise. We do something like F1 equals, UK. This looks, I mean, I don't know if we did RK3 explicit, we did RK4, right? And that's 4 calls, and that's not a surprise. This looks pretty similar. I'll write it for fun, why not? F3. Okay, so you do this, and then you kind of do this weighted sum thing. So you kind of like average all these dynamics calls, right? This looks a lot like RK4. The details are a little different. So that's 3 dynamics calls. Okay, let's look at this thing now. The Hermite-Simpson thing that we just did. We have this one equation that does involve 3 dynamics calls. But if we look at this carefully, these 2 calls at the endpoints get reused between this time step and the next one, right? And the previous one. So it turns out, like asymptotically, there's some endpoint things that happen, right, that are extra, but asymptotically, this only requires 2 dynamics calls per time step. So this is like half the computational cost-ish, or 50% savings, right, over doing the kind of one of these classic explicit methods. And it turns out they work better anyway. There's sort of other advantages. And usually these dynamics calls and the associated Jacobians are the dominant computational cost in these methods. So this is a big win. Okay, any questions about any of this crazy stuff? Yeah.
Why do we do the dynamics constraints at the midpoint as opposed to endpoints? Is doing it in the midpoint what lets us reuse dynamics calls?
So doing it at the midpoint is kind of what lets you, yeah, but the reason is basically when I define a spline, we didn't talk, maybe I should have like gone into more background on splines. So like the deal with a spline is I have a bunch of points I want to connect with a smooth interpolant. And to make it smooth, what I do is I enforce that the points match and that the first derivatives match, right? So in this situation, I'm enforcing that the xk's match at the 2 splines when they connect, and that the x dots match. And that's just the matching condition from the spline, right? So there's no dynamics there. I mean, I already have like a condition that the x dots match at the knot points just from the spline definition. So I can't really enforce the dynamics as well, right? So what I do is I enforce the spline matching conditions on x and x dot, and then I enforce the dynamics in the middle. Does that make sense? Yeah, and basically like if you start with like a initial state and a goal state, then that takes care of the boundary conditions as well. So basically then you've only got sort of like n-1 dynamics, sort of things. The number of unknowns and number of constraints works out is basically what I'm saying. Yeah. Does that make sense to everybody? Ish, okay. This was a lot. Hopefully that some of that stuck. Okay, now we're gonna do fun stuff. Does anyone have any other questions on this before we like do code things? Yeah.
Are both the like states and their derivatives decision variables?
No. So the states are the decision variables. The x's, which typically in robotics applications includes, position, velocity, whatever, right? So that's what your decision variables are. The x dots get computed as part of the constraint stuff. They're not explicitly in there. We wrote them down as part of this whole spline thing, because the standard spline stuff is you make the x dots, you make the x's and the x dots match across where you glue together the splines. And then I did it because the x dots are also what our dynamics constraints are, right? So what I'm basically doing here is saying at the endpoints of each cubic spline segment, the x's and the x dots have to match between neighbors. And I can compute those x dots implicitly based on the x's, right, and the dynamics. That's kind of what's happening. So I enforce those matching conditions, and then I enforce the x dot computed at the midpoint of that cubic spline has to equal my dynamics function evaluated at that midpoint. So that's it. That's everything. It's basically matching x and x dot matching at the knot points, and then dynamics enforced at the collocation point. That's where those names all come from. Is that good? Everyone good with that now? Yeah.
So why are we doing this? You said it's better to do it when we're doing the NLP programming.
Yeah.
To do collocation. Okay.
It turns out this is more efficient and also like more stable and more accurate than using a standard Runge-Kutta method when you do direct collocation, when you're doing a direct big NLP solve, as opposed to the dynamic programming stuff. Okay, yeah. So basically, you can't say anything about the dynamics at other points. What we're doing here is it's similar to, so really every Runge-Kutta method that you write down is doing something similar to this. It's a little more explicit here, but actually every Runge-Kutta method is implicitly basically fitting a spline to the dynamics over a time step and then evaluating the dynamics to get like x dot and you're really fitting a polynomial. Like RK4 actually fits a cubic polynomial as well over the time step. So most of these methods are doing something like this. And you can only really enforce the dynamics at a finite number of points in some interval, right? And what you're doing is basically assuming that the solution to the ODE is somewhat smooth and that it's well approximated by a smooth polynomial interpolant over this time step, right? That's what all Runge-Kutta methods are doing. They're all assuming that over some small time step, the things are smooth enough that it looks roughly like some polynomial and you fit a polynomial. Have you ever seen standard Runge-Kutta methods derived like RK4 or any of these things before? No. Yeah, so I mean, I did it in my class last semester in the dynamic simulation class, but like they all kind of have this flavor of like fit a polynomial over the time step. Here we did it very explicitly, and you see it's a cubic spline and all this stuff. It's less explicit some other times, but like this is kind of always there. And you have to make some choices and some approximations because these are, at the end of the day, these are nonlinear differential equations that don't have exact solutions, blah, blah, blah. So this is kind of what we have to live with. Does that, I don't know, help? Okay, let's look at some code and stuff before we get out of here. Here's our favorite acrobat yet again. Oh, wow, that's really ugly. Okay, cool. So here's what we're dealing with. We're gonna do the acrobat again. 10 Hertz samples, 5-second horizon. Here's the dynamics constraints that we just derived. So we've got sort of two neighboring knot points, both the states and the controls. And then inside here, I'm not doing this the smart, efficient way. I'm doing it the dumb, inefficient way because it's easier to write down. But basically, yeah, I'm just plugging into the equations we had before. So I'm evaluating the midpoint according to like the spline rules. The x dots I'm getting by evaluating the dynamics. This is x dot at the midpoint. And then, this is the dynamics evaluated at the midpoint. So really what we're doing is, right, we're like basically evaluating x dot at the midpoint according to the spline, and then evaluating x dot at the midpoint according to my dynamics function, and saying those have to equal each other. At the end of the day, that's what this is, right? Is that cool? Everyone cool with that? Okay, so that's that dynamics constraint. Cost, same kind of stuff we did before. Quadratic, whatever. I'm actually, going to use these this time, unlike last time. This is the entire dynamics constraint now. So I have to make this work, I'm stacking up all the x's and u's into a giant vector of decision variables. And this is basically just looping through that giant thing and writing down, stacking up all of the dynamics constraints across all the time steps now. So that's, yeah, evaluating over the whole trajectory. Here's the constraint function. This is just for the solver interface, basically, but this is just dynamics constraints. And then this is initial state constraint and goal state constraint. So actually one difference between this and DDP. In DDP, I was using a terminal cost to get it to stand up. Here, I'm actually going to put in an explicit goal equality constraint at the end of the trajectory to get it up to the top. This is all solver interface stuff that is not important, but annoying and, whatever. We're using IP-opt, I should mention here, which is one of the standard solvers. This is just the interface in Julia that is how you have to talk to the solver. Nothing particularly worth looking at. The only, I guess, thing that might be kind of interesting here is, so you basically pass it the cost and then the gradients and Hessians and stuff. Here, we're using auto-diffing to get all that stuff as usual. Yeah, I don't think there's anything worth talking about in here. Solver tolerances, whatever. Is there anything worth saying here? I don't think so. Okay, cool. So initial and goal states, we write them down, and in this case, they become constraints, right? Initial guess, nothing smart, like zeros, ones, something like that. Now we're going to call a solver. And that's going to take a minute. And I think I ran this before, so we can probably just look at it. But kind of slow.
Exactly. The whole point of us doing this direct correlation method in the first place is that it's more stable. We're trying to optimize features, right?
So that's one of the reasons. These are basically like, this is just like one of the major two options. You can do like DDP stuff, you can do direct collocation stuff. And there's some trade-offs. We'll get into the details of the trade-offs. This is one of the standard algorithms. Like there's reasons to just do this. Like in general, like the DDP stuff and this stuff are kind of on par with each other. And depending on your application and what you're trying to do, like one or the other might be preferable. Yeah, I don't know. You should know about both of them and you should kind of know which one to pick, when. Okay, so we just solved this. That was kind of slow. Generally, these do kind of better than that. I don't know. I probably gave it a bad initialization and stuff. So here's the trajectories. I don't know. Not too dissimilar from the stuff we were doing before. We can animate it before. Oops. So this looks pretty much like exactly what we got last time with DDP, because I had the same cost functions and stuff, basically. So here's where this kind of gets interesting. So we talked about infeasible starts and things like this. Here, and I mentioned this last time, but it wasn't maybe super obvious. So I have a good solution right now, right? If I go ahead and just run this again from this solution, like it should basically converge instantly and take like no time because I'm handing it already a good solution. So we can do that real quick and see what happens. Hopefully that does what I think. But then what we can also do is, which I'll try in a sec, this is going really slow. I can do things like, so right here, I gave this a guess that was kind of dumb. I can give it, for example, a guess where, let's say, I don't know, for some application, some robot, let's say I'm able to draw some cartoony, okay, so there it went. This still took a long time. I don't know what the hell I was doing. I don't know. Anyway, let's say for whatever reason, I know like one element of the state vector. Oh, I didn't, yeah. Okay, let's say magically, I know, like, so what I'm gonna do here is give it an initial guess that is my solution only for the first element of the state vector plus some noise. So I'm not giving it the whole state. I'm not giving it a dynamically feasible guess either, right? Like this doesn't obey the dynamics anymore. I'm just randomly giving it, stuff. But this is obviously in some kind of like norm distance sense closer to the answer, right? I'm getting it in the ballpark, that kind of thing. But it totally violates the dynamics constraints, et cetera. But now watch this. If I do this, it just finished like instantly. 24 iterations took like a second, right? And we can plot what that looked like. So I gave it this guess and like zeros for everything else. So I only gave it like one component of the state, but that was enough to warm start it to get it super close to the right answer such that it converged really fast. So this is one of the major advantages of this over DDP methods. DDP, it rolls out, right? So I have to give it basically an initial state and initial controls and let physics do its thing to get my initial guess. Here, I can hand it whatever I want as the initial guess. And the dynamics are all represented as these equality constraints in the problem setup. But that initial vector that I give it of states and controls can be anything that I make up. It doesn't have to obey the constraints necessarily, right? And the solver will figure it out. And like at convergence, it will obey the constraints. So here, I can just draw some cartoon, guess trajectory that I can make up, that I can get from a sample-based planner or some other algorithm entirely that gets me close, gets me in the ballpark, and you can just throw it in here and let this thing go. And often that can be a big advantage on complicated problems where you may have some heuristic or, intuition or other algorithm like kinematic planner that can get you somewhere in the ballpark. That's it. Cool. Questions, comments? Yeah.
So here, if you start from an infeasible start and then you stop before convergence, what do you get like one design?
Yeah, so that's the counter to what I was just saying. Yeah, like DDP, if you stop early before it converges, you still got something reasonable that you can maybe execute, even if it's suboptimal. Here, if you stop early, it doesn't necessarily obey the dynamics constraints. It only obeys the dynamics constraints at convergence. So if you stop early, you might have something that's completely unphysical garbage that is not, able to run on the robot, which is bad.